Okay, maybe we can start. In the last lecture, we kind of rushed through this Toric model. So maybe let me just summarize a little bit. And so we are emphasizing that we are studying this so-called long-range entangled states. And one way to get the long-range entanglement is to make a superposition, but not superposition for everything, superposition for a part of a configuration. So one natural choice is that one can choose a spin down as a string of spin down, then consider superposition over all the strings. And this picture really led to this Kitev's Toric model. So we actually have this microscopic soluble model to realize this string superposition for all the loops. And so Toric model have this Q term and the F term. Q is a product of sigma z around a vertex. The F term is product of sigma x around the plaquette. These two terms commute. So this model is exact soluble. And the QF just has eigenvalue plus minus 1. So the common eigenstate for plus 1 is ground state. So whenever this operator became from 1 to minus 1, so that's an excitation. And the funny thing about this excitation is that they are not like ordinary spin flip. The ordinary spin flip is also like a SD go from 1 to minus 1, but that can be created by the single operator. And here we apply the single operator to any spin. Then you find you flip 2Q or 2F. You can never flip one of them. So it turns out that this flipping sign excitation can only be created in pairs, and they are created by this so-called string operator. So we can find some string operator which only flip this Q or F at the end of a string. The string can be product of sigma z if a string on the dual lattice, or product of sigma x if a string is in the original lattice. So that's kind of a picture we have last time. So here I would emphasize that this topological excitation are associated with the string operator. We are created by string operator. So that means the middle of string create nothing. It commute with all the term in the Hamiltonian. They don't create anything. Only end of string you create something, some energy bump. Okay. So because middle of string commute with a Hamiltonian, that's like a symmetry. So this is yeah. So this is it's a string from a loop. They just commute with Hamiltonian. This symmetry. This is really the higher form symmetry introduced by this Gaiotto, Kapustin, Seiberg, and Willett. After this paper, the things whole field take off. It became very, very popular topic. And but here you can see clearly that this existence of a string operator and existence of a topological excitation somehow appear hand in hand. They appear together. So there's a connection. And this connection actually is important, so which we are going to emphasize here. And another thing we want to emphasize is that it's about the issue about this emergent higher symmetry. And Patrick last week asked the question, the Toric model is a very fine-tuned model, with a 4-body interaction, 6-body interaction. For generic lattice model with 2-body interaction, we may not have a higher symmetry at the lattice level. And but however, the ground degeneracy from this Toric model can be viewed as a spontaneous breaking of a higher symmetry. And we know that this ground degeneracy is robust against arbitrary perturbation, including the one which break the higher symmetry at the lattice scale. So this really hint at general results that maybe the emergent higher symmetry is exact. So that led to this exact ground degeneracy, even when you break the higher symmetry at the lattice scale. So usually for zero symmetry, we usually have the following picture. That's suppose we have emergent zero symmetry at the low energy. That means the breaking of zero symmetry may go to like energy to some power. At finite energy, you have some finite breaking, but as energy go to zero, you get a better and better symmetry. And you may also have a term which is like a system size dependence. Okay, then when system size go to infinity, this energy part survives. So we get this intuition that the emergent symmetry is always approximate at the low energy. Only when energy go to zero, you get exact symmetry, but not at the finite energy. Then there's a belief actually in this paper which is going to appear next Monday. That is for the higher symmetry, emergent higher symmetry, things are different. We don't have this energy term. We only have a system size term, which may be exponential or maybe algebraic, maybe different situation. I think in general, for gap system is exponential. Then as L go to infinity, then we really have exact emergent higher symmetry, really exact. Yeah. So this may be a general statement. So after this statement is consistent with this what we believe that the ground state inertia in a symmetry breaking phase, in a spontaneous symmetry breaking phase of higher symmetry, that's led to ground state inertia, and that ground state inertia is exact even when you break the symmetry at a large scale. And but this statement is a little general. That even in the confined phase, in a non-topological phase, we believe this is also true. So that means this emerging higher symmetry may exist at the transition point, transition from this topological phase with degeneracy to another phase without degeneracy. This critical point may also have this some exact emergent higher symmetry, and so this emergent higher symmetry may control the phase transition, low energy dynamics. So actually, this is the main topic of this sequence of lecture. Try using symmetry to see what you can learn about the low energy dynamics. And it's also important in the sense that this higher symmetry become useful in kinetic matter because at the beginning, I also have a similar thing. If you don't design the lattice model, you don't have higher symmetry, why bother? But actually, emerging higher symmetry is exact. So therefore, it's really useful, even though we don't have a higher symmetry in the lattice scale. But at the low energy critical point, I think like that, we really have exact higher symmetry. Then it's very, very useful. Yeah.
I was wondering about whether you can make this emergent higher symmetry and in particular scaling well defined also in gapless state, but in terms of the gapless point of the
yeah. Yeah, this statement is really about that. This paper really is about even for gapless states, they can exist. The sort of a gap state, so there's there's some rigorous proof to say this ground state inertia is robust against the arbitrary perturbation. I believe that the proof can be translated into the one to show that for this gap state, emergent higher symmetry is exact at the low energy. But however, the validity of the result maybe is broader. So even in the gapless point at the transition point, we still have that. So that makes it useful in a sense we can use in this emergent higher symmetry to constrain the critical point. Yeah. So that is but somehow, so after this we find that only zero symmetry is special. It's so this intuition from zero symmetry does not work. For higher symmetry, they always exact. The only zero symmetry is not exact. There's something. So maybe near the in the last few lecture, I probably develop enough. We can just study this phenomenon. Here, just present these results. Yes.
For this consideration, do you care whether it's discrete symmetry or continuous
symmetry? Okay, the result is more reliable for discrete symmetry. For continuous symmetry, things are trickier, and so this result is exponential. I think is for discrete symmetry. For continuous symmetry, there could be this a power law. And as a belief, we believe it is also true for continuous higher form symmetry, but there is a trick here, and in a sense, in this paper with Hastings, we show that even for the Coulomb phase, the ghost, this photon, the U1 gauge boson, the gapless gauge boson is robust against arbitrary perturbation on lattice scale. And at that time, we say this U1 gauge symmetry is robust against arbitrary perturbation. So now that one probably can translate into some kind of continuous higher form symmetry is robust against the arbitrary perturbation. So, but there, the error we find is algebraic, not exponential. So actual argument is kind of different. Yeah. So continuous symmetry is always trickier. Yeah.
Let's just talk about this case where you have a Z2 topological order and transition into a trivial one.
Yes.
So that one can be interpreted as breaking of these one-form symmetry.
Spontaneous, yeah. Yeah.
And then on the topological side, I can see that there's stability of topological order, so emergent symmetry is exact. On the trivial side, is there a similar thing?
Yeah, there are symmetrism. The things a little bit tricky is that so actually maybe since this question, yeah, I can say that. So you can see for the Toric model, we have a 2-1 symmetry. And I think when you do the transition, you can break, it's condensing one of a thing. So I think you either condense E or condense M. Okay. And when you're condensing E or condensing M, then the only one of the symmetry remain to be emergent. Suppose you condensing E, but M may have high energy. Then near transition, you don't have both, but you only have one. The other one is have high low. The energy scale became low. Then I would say this a single surviving symmetry is effective in both sides of transition. It's exact. It's emergent symmetry is exact on both sides of transition and including at the transition point. Then the funny thing is that then the other side of transition, this symmetry is not broken, so became symmetric states. So there is a possibility that you may have emergent SPD states. So you may have SPD states for this emergent symmetry because this emergent symmetry is exact. So the other side of transition can be trivial states for this symmetry, and dependent situation could be the SPD states for this symmetry. And so this confined phase may have non-trivial SPD order for the emergent symmetry. And that means in the confined phase, maybe the boundary may have some non-trivial boundary. And so this is yeah. So there's a consequence. Yeah.
I have another question.
Yeah.
Actual phase diagram, the actual Anomaly model is two. You say there are two transitions. One can restore one symmetry or the other. Right?
Yeah.
But actually, they're continuously connected.
Yes.
So
yes.
How can you connect it?
That's true. And so they so the point is following that yeah, so maybe later I'll discuss this in detail. But what have is you have a Higgs transition or confined transition, and actually for the Higgs transition, the confined transition, they have different emergent symmetry, and all these two phases are connected, but somehow in the middle somewhere, this emergent symmetry no longer break down. So yeah, so this is a string indeed, and so there's a switching. Yeah, this part is also a strange part, and also is a part which we don't quite understand. that we claim in some region there is an exact emergent symmetry, but this exact emergent symmetry can disappear without phase transition. This part is kind of strange. Indeed, you know, certainly if there's a phase transition, then you say exact emergent symmetry disappear is more reasonable. But yeah, indeed, we kind of claim this may happen because there's other argument to say in this neighborhood the emergent symmetry really they are exact, and but away from the neighborhood, far away from the neighborhood, how things break down is not very clear.
So
but
one of the symmetries disappears, right?
Yeah.
Electric remains, right?
Yeah.
Maybe the statement that it's exact is no longer true. Maybe it's actually only an approximate.
Yeah, if the approximate is a thing, but okay, let me put it this way. What we think is following. You know, these symmetry are generated by these loop operators. Okay. So in the confined phase, this symmetry is still there. It has a loop operator, but the loop operator have some thickness. And then when you go away from nice region, the thickness became broader and broader. And so the claim is that at certain parameter regime, the thickness of a loop operator became infinitely diverging. And so without phase transition, yeah. And this part is kind of strange, but the thickness of a loop operator which you can perform the symmetry became too fat. And or maybe the secret, yeah, this part I really don't know. Yeah. So the kind of what we understand is that in certain two neighborhood, we can define this loop operator with finite thickness to perform the symmetry. But far away from that, we don't know whether this loop operator can be defined, not defined. But the conventional wisdom is that since these two regions not connected by phase, it's connected smoothly, not separate by phase transition. That is a puzzle, yeah. And so it could be either way. Maybe this puzzle is very important and is more reliable. So maybe there's some error in our argument. If you think that our argument is more reliable, then yeah, then this fattening of loop operator without phase transition maybe is a acceptable consequence. Yeah, but this is indeed really something we really like to understand directly. Right now we don't have this transition regime. What happened to this transition regime? Yeah, yeah. This claim is kind of strange and also kind of strong, but yeah, but at the moment I think yeah, maybe let put this there to see what's going on. Yeah.
Is there some recent work that you point out X and Confined are related by some boundaries?
It's a little bit, you know, this variance work. It's a little bit different, you know, and yeah, I haven't. Yeah, I think that the argument is somewhat different. Yeah, yeah. But on the surface, it seems similar, but the detail seems different. Yeah. Okay, so so here we say that because in the Toric now we have E particle, I have M particle. Actually, we have F particle. Let's forget F particle. Just E particle, M particle. So they are created by string operator, two string operator, and each string operator corresponds to the symmetry. So so we have this 2Z2 symmetry. Okay, then it's very tempting to think, oh, we have a 2Z2 symmetry, 2Z2 symmetry, they combine into this product of a higher group. But actually, the higher symmetry and in general have a more data. Their relation is more complicated than just ordinary group symmetry. In a sense, they can be viewed in this way, like I think I mentioned this, that the loop operator which generating those symmetry may not commute. Okay, so the two loop, if they intersect, it may have minus sign if intersection is a minus, is odd. But however, you may say, oh, this is trivial because two loop only intersect even point. So this sign always a plus one. There's no minus sign. But actually, for two non-contrastive loop, if a torus one loop go this way, another loop go that way, then they can intersect one point. So for non-contrastive loop, we can have this minus one. Okay, so this sign is actually turns out to be is viewed as an anomaly. Yeah, this kind of new relation between two symmetry. Usually we just have two symmetry A, symmetry B, we just put them together. But actually, the symmetry transformation of the two symmetry may have actual relations, and this actual relation non-trivial. Then that's a new structure of the symmetry, and this new structure can be called anomaly. So that's one way to understand anomaly. But anyway, but this word is also now is too much, is too widely used. So anomaly can mean many different things. So here we just generally refer to whenever you have non-trivial relation, we say there's anomaly. Okay, and so there's another way to see this without consider contrastive loop, because we'll define anomaly using contrastive loop is things depend on space-time geometry topology. So let's consider the following. We introduce what's called the patch symmetry operator. We know that when we do symmetry transformation, usually we do symmetry transformation of the whole space. But we can consider just doing symmetry transformation on the patch, not in the whole space, on the patch. And then the boundary is something arbitrary, we don't care. But the middle part is performing symmetry transformation at least. Here, for this one symmetry is generated by this loop in 2 dimensions. We can also consider patch. The patch of loop is open string. So we can have open string operator. So this is really just a 2 open string we discussed here. So that's one of open string, and that's another open string. And then when these 2 operators, now you can see that these 2 operators can be when they overlap, you can see so this red string can be go like this. Then they intersect with a blue string on this single qubit on this point. And on this qubit, the red string is a sigma x, the blue string is a sigma z. So you can see they on that commute. Okay. So the picture is that using this patch symmetry, just an open string operator, you can more easily detect this anomaly. Means these two strings when they straddle, when they cross, they on that commute. So this seems more convenient that we can using patch symmetry operator and consider their algebra and to see whether this symmetry have anomaly or not, whether they have special relation or not. Yeah, this became pretty general, and so it's applied to ordinary symmetry, also applied for higher form symmetry. We can using patch symmetry operator. It's more easy to study their all kind of algebraic relation to see the 2 symmetry are not independent. There's some relation between them. So that's the idea. Yes.
You always find patch symmetry operators.
Yes.
Like you always find it.
Yeah. Yeah. So I feel that the patch symmetry operator maybe is a better choice to do symmetry. The reason is that in the many-body system, our Hamiltonian is a local, and only local term. We just in the space like each Hamiltonian term is symmetric or not symmetric. We don't need a transformation on the whole space to tell that. The transformation on the patch can select local operators as long as this operator is far away from boundary. And so therefore using patch operator to describe symmetry have some advantages exactly like this. It's much easier than once you use the patch symmetry operator to generate all different symmetries. then you can study their algebraic relation more easily, and can review this non-trivial algebraic relation. Actually, in particular, this is important here, because this kind of relation have another interpretation. That is, we know this patch symmetry operator, this string operator, they generate anyang on the two string end. And actually, this relation of string operator implies that an anyang at the string end have a non-trivial mutual statistics. So this also led to the picture that we say that in this case the symmetry are generated by string operator, and the annual string operator correspond to quasi-particles. If those quasi-particles have non-trivial statistics or non-trivial mutual statistics, that means those symmetry either have a mixed anomaly or each symmetry have its own anomaly. Yeah. And so when you have a set of anomaly-free symmetry, that means the particle generated by end of string operator all behave like boson and all have trivial mutual statistics. So this is one way to understand this so-called anomaly-free symmetry. Yeah, the bottom line is that the symmetry is richer than we thought, have this additional feature. And this additional feature can be captured by statistics of end of a string. In more general, if your symmetry is a membrane, then the boundary is a string. Then the string may have their more generalized statistics, and so that's kind of like a more general case. Yeah. But from this example, you can see how those actual feature of symmetry can appear. So this is just an example of that. Okay. So this is just another thing to emphasize that whether symmetry is anomaly or anomaly free depend on whether the end of a string operator have a statistic or not. And this non-trivial statistics for end of string operator can be detected by some algebraic relation of the string operator. For this commutation relation tell you the mutual statistics, and to detect self statistics is trickier. Then we have to consider this TAB. This string operator is like a hopping operator, hopping particle from one end of string to another end of string. This open string operator can be viewed as a hopping operator. And then we talked about this last time. That's when you have a three hopping operator in different order, then you may hop this black and white to two different final configuration with the black white exchanged. So therefore, the different phase of this three hopping operator is red, green, blue, or blue, green, red. It's just different phase. You can just red and blue get exchanged. The different order of this hopping can lead to different phase, and this phase detects self statistics. So this is the more complicated algebraic relation than this one. But still some algebraic relation between those open string operators. You can detect that. Yeah.
Can I ask?
Yeah. Yeah. So that's the next next question. Yeah. So actually, there's a lot of terminology. So higher symmetry just a abbreviation of higher form symmetry, but you can also use it differently. The higher form symmetry actually is introduced in this paper. So they are really a symmetry described by higher group. Okay. I don't know. Yeah, actually, yeah, I don't know what is higher group, but I do have a paper. That's my study notes to learn what is a classifying space of a higher group. That is easier. And yeah, probably yeah. Let me see. Should I? Yeah, I don't have a plan to go into that. Yeah, it's a maybe let me put it this way. No, I can answer this question in this in a more maybe elementary way. It's the following like this. Okay, now I can explain the following. So the end of a string is onion. If those onion is abelian onion with a quantity dimension 1, then I think it's a higher group. I try to define higher group this way. However, if end string is a non-abelian onion, then that is beyond the higher group. So higher group imply that those onion at the end of string must have quantity dimension 1. So this is really the thing. You can see that if those onions at the end of string have a non-trivial statistics, that's a feature of anomaly. So non-trivial statistics or non-trivial self or non-trivial mutual statistic is a feature of anomaly. However, there's another thing, whether this onion have a quantity dimension 1 or don't have quantity dimension 1. Then that's a feature, say, whether it's within higher group or beyond higher group. So that's one way to that's maybe I don't know whether this is easier. So then you can see that, but this only for the particle. Then if you higher symmetry generated by membrane, the boundary will be string. Then presumably string also have this notion of a quantum dimension. Then if a string have a quantum dimension 1, then that's a higher form symmetry or higher group symmetry. If it's beyond the quantum dimension 1, maybe that's a beyond the higher group symmetry. Yeah, that's my understanding. Yeah.
One helpful or not helpful is to define high group, just say it's a higher category. It's one of
Yeah. So then there's issue. What is higher category? In my explanation, I already used this quantum dimension. So actually, I'm going to explain what is quantum dimension. Yeah, and so this really this type of symmetry either can be anomalous or anomaly free. That's about the braiding phase. Then whether this boundary have a quantum dimension 1 or not quantum dimension 1 is about invertible or not invertible. Yeah, that is a feature. So yeah, if a boundary is a quantum dimension 1, then the symmetry is invertible. So it's more like a group or higher group. If a boundary have a more than 1 quantum dimension, it's more general. And so it's not invertible, it's not higher group. Yeah. And but this so yeah. So I need to explain what is quantum dimension. Okay, the quantum dimension actually there's an easy way it's easy because spin 1/2 is an example of a non-zero quantum dimension, not non-zero, non-unit quantum dimension. They have 2-degree freedom in a sense that the spin quantum state from a 2-dimensional vector space. All different spin states from 2-dimensional vector space, then we say quantum dimension is 2. So quantum dimension is a dimensional vector space formed by internal degree freedom, and that's it. Okay. And if quantum dimension equal to 1, that means the particle have no internal degree freedom. So we call the abelian onion. And if a end of a string is abelian onion, that string generates a higher form symmetry or higher group symmetry. Okay. However, we have some more, but we do know that there are examples of non-abelian onions. So Toric code is only abelian onion, but there's other topological phase with non-abelian onion. They are also generated by string operator. Then the string operator generates non-abelian onion. This string itself would generate beyond the higher group symmetry. Yeah, so you may say maybe higher symmetry including this beyond group higher symmetry, this higher symmetry. You can also say so. So therefore, if a quantum dimension is bigger than 1, it's a non-abelian onion. And the physicists may not like this definition because that means electron is a non-abelian onion. We say it's a fermion, it should be abelian. I don't know, but mathematicians really think this is more natural. So we should call electron non-abelian onion. But for physicists, maybe you can say if a dimension is not integer, it's non-abelian onion. If integer is still more ordinary. So actually there's some subtlety here. Actually, this method is there. We know the spin up, spin down electrons are degenerate. When you're braiding a spin 1/2 electron, two spin 1/2 electrons together, in principle, you may have a non-trivial rotation matrix rotating spins. And in general, we should worry about that. Okay, so so actually, I don't know experimentally whether one can realize some kind of spin 1/2 electron which can see non-abelian feature. So basically, non-abelian feature is the following: we have two spin 1/2 electrons, they're far away, but then these two electrons can be combined to spin singlet channel and spin triplet channel. Then you'll find that when you're braiding these two electrons, you get different phase is two electrons in the spin singlet channel, and another phase is two electrons in the spin triplet channel. So that is the true meaning of non-abelian statistics. That is for spin 1/2 electron, the braiding phase depends on whether they combine to a spin singlet or spin triplet channel. And for usually for electron, spin singlet, spin triplet, they have same braiding phase, just a pi. Then we say they are abelian, not non-abelian. Okay, but I don't know whether experimentally one can realize situation where spin singlet, spin triplet have a different braiding phase. Then you can claim you make an electron into a non-abelian particle. Okay. And what is the most amazing is that this non-abelian anion, the quantum dimension can be non-integer. Okay. So one well-known example is the non-zero mode. I think people have studied a lot in terms of topological quantum computing. So if a particle, say, not carry spin 1/2, but carry something we call non-zero mode, So non-zero mode, like spin 1/2, like a 2-degree freedom. When we say carry non-zero mode, we say this particle would carry 1/2 degree freedom, or 1/2 qubits. In the following sense, it have quantum dimension will be square root of 2. It really means that when you have n Ising anion, this kind of non-abelian anion, the total dimension for vector space to describe this internal degree freedom is 1/2 square root to the nth power. And the n is integer, so this one is always integer. So when you have n anions, the total internal degree freedom forming this kind of a dimension of vector space. Then when n go to infinity, you say, oh, this square root 2 is determine how things grow. We say this square root is called internal degree freedom. So that's how we define this quantum dimension. So this one exists, and so this is a non-abelian anion. So once you have that, then the corresponding string operator would generate some kind of higher symmetry, but beyond higher group higher symmetry. So we can see that the symmetry can be very rich. But on the other hand, the symmetry can also get can be understood more easily by their patch operator and by the particle at the end of a patch. That's a way to view the symmetry more conveniently. That's yeah. Is there any question? Okay. So that's just some general discussion of symmetry. Okay. This part is supposed to be this a microscopic model of a topological order. So let's just quickly go through some other system which produce topological order. So Toric code is one of them. But actually, the first one we know is actually is a Laughlin states describing fractional quantum Hall states. Here we have electron in 2-dimensional plane. So the Z labeled the electron coordinate. So this is a Laughlin wave function describing a particular ground state of an electron in magnetic field. Okay. So this one actually is this manifold state is another example with a long-range entanglement with topological order. Okay. So to see this, we see that if you remove one electron, make a hole, what happens that we just renaming say Z1 into Kasi. So Z1 is no longer calling the electron, just a mark. So therefore, this wave function describing a hole an electron like a hole, absence of electron, and this hole is at the C. But once you have this whole wave function, you can easily say, I can split this C into 3 or into m different C. So each one only have a single zero, not m's order 0, single 0. So now you can see that this wave function describe a quasi-particle like a 1 over m of the electron. Okay. So it's a carry charge 1 over m. Okay. But this one also carry flux 2 pi. Means if another electron go around this C, the wave function changes by 2 pi. So therefore, this quasi-particle behave like a 2 pi flux to other electron. Then we have this standard argument that actually this quasi-particle is a bound state of a charge and a flux, which can have fractional statistics. Because when you have a flux charge bound state, suppose this middle one have a flux and the second particle have a charge. When the charge go around the flux, then we get a phase of a charge times the flux. But to describe exchange statistics, we only need to do we just need to do half rotation, not the full rotation. Okay, so we just do the half turn. Okay. Then plug in the number, charge is 1 over m, flux 2 pi, and then do the half turn, we get a pi over m statistic angle of exchanging two quasi-particles. Okay. So this is a kind of a so-called a canonical way or standard way to compute statistics using cartoon picture. And you may say, oh, you're missing a factor 2, because each particle have charge flux bound states. Here you only consider charge around the flux. You should also consider flux around the charge. So it's another contribution. So yeah, indeed there should be factor 2 there. But in this particular case, happen to be there's no factor 2. So this is a very famous factor 2 problem. What I try to say is that in a superconductor, you have a flux, you have a charge. In a superconductor, then you do have this factor 2. In the superconductor, when you consider in 2-dimensional superconductor, when you consider flux charge bound states, and you do have this factor 2 to compute the statistics. But in quantum Hall states, for some reason, there's no factor 2, and I have to do a more careful calculation to see, yeah, this is the right result. But anyway, so this is just a standard picture for the Laughlin states, and why Laughlin states have a anion, and then you can imagine these states should have a higher form symmetry, because these anions are abelian, so it's a higher form symmetry, describe a higher group. And because this anion have a non-trivial statistics, so this symmetry should be anomalous. So the string operator generating 2 anions, this string operator should also generate this emergent higher form symmetry in these Laughlin states. Okay. And then we can do the more general wave function. So we can consider a kappa layer system and have a kappa by kappa K matrix. Then you can write down this coupled layer wave function in this way. So intralayer KII, the diagonal matrix element of KII, describe an intralayer zeros. So intralayer electron have a 0 given by KII. But the interlayer, between I layer, J layer, their zeros, wave function have zeros given by Kij. So Kij tell you the interlayer zeros. There's interlayer repulsion, give you interlayer 0 in the wave function. Okay. And so in this case, the excitation at the C are labeled by an integer vector. It's similar, this the component of this vector just a different layer. So that means that this particular quasi-particle is 0 in the electron wave function, but the order of 0 is given by this Li, different component of this vector. Okay. So then we have this quite a systematic theory, which we have a K matrix, which is symmetric integer matrix, describing wave function. We have a quasi-particle labeled by these integer vectors. So very systematic way to describe it is a topological order. And we also have the condition that this the quasi-particle labeled by different L may be equivalent if they're different by column of a K. If this L equal to column K, then this quasi-particle actually is the electron itself. It's original electron. So this regarded as not fractionalized, regarded as trivial. The fractionalized quasi-particle are labeled by this L, but with this equivalence relation, because these two L differ, but electron is regarded as the same. Okay. So if you go through the math, we find the different class of fractionalized quasi-particle just given a determinant of K. So there's a fractionalization given a determinant K. And so this became a theory we say is maybe the most general abelian topological order can be described using this kind of matrix or the lattice. This is really a lattice theory. Okay. And so then the self-statistic, the mutual statistics can be computed using K matrix, like K inverse with L on between, we get these statistics. Mutual statistics such as L prime, two quasi-particle L prime, have a mutual statistics also given by this. So this is kind of interesting, simple relation. And also this quantum houses have a boundaries. Boundary may have a gapless edge mode. The number edge mode is usually there's many boundary, but the one of a canonical boundary have a K kappa edge mode, and the eigenvalue of a K determine whether it's a left mover, right mover, depend on sign of eigenvalue. If eigenvalue have a positive sign, that's right mover. If eigenvalue have a negative sign, they have a left mover. So this gives you some general theory for this multi-layer quantum Hall states. And the one motivation, for example, like this, if a K is a 1, 1, so there are two positive eigenvalue, that means have two modes, but both modes are right moving. So this is really integer quantum Hall state with two fields along the level. Yeah, we have a two edge mode. So this just agree with that. And one motivation to study this more weird case, this general case is have this weird example. There's an 8-layer quantum Hall states which have a non-anions. It's very strange because we have this particular K matrix whose determinant equal to 1. And this K matrix only appear, the smallest one only appear in the A dimension. You know, in 1 dimension, yes, 1 dimension is simple, just a 1. But 2 dimension, 3 dimension, such matrix do not exist. They exist first in the 8th dimension. Oh no, sorry, I was wrong. 1 is illegal. I need to have the even diagonal because there's the even diagonal means it's a boson. Yeah, because the bosonic quantum Hall state, even diagonal means in the same layer, the wave function have a even order 0, means they are symmetric. Yeah. And for even diagonal boson is a K matrix. They only appear. The first one is 8 dimension, and next one is 6 dimension or 24 dimension. So they exist. Because determinant K equal to 1, that means these quantum Hall states have no fractionalization. All the excitation are electrons. There's no non-trivial excitation. So you can say it's almost trivial. This topological order should be trivial because no anion, nothing there. But this one have a non-trivial edge states. They have 8 right moving edge states. Okay. So the boundary is non-trivial. And even though the bulk is trivial, but the boundary, there's no trivial boundary, no gap the trivial boundary. The only chiral boundary exists. So this became a special topological order, which is this topological order will play important role in the later development of theory. So I just gave an example here. It's called the invertible topological order, which we'll discuss later.
So I have a question.
Yes.
So you said that the sign of the eigenvalue,
Yeah.
tells you the chirality. What about
Exactly.
What about the number?
Oh no, the number is like this K matrix. There are 2 eigenvalues, both with plus sign. That means have 2 right mover, no left mover.
What does the magnitude? Does that number matter? What does that number?
Doesn't matter. Yeah, just a sign. So actually, more precise, actually using sign is a bad way to say that. More precisely, it's following. The number of right moving mode and the number of left moving mode, they are topological invariant. The total number can change, but the difference cannot change. And this difference corresponds to signature of a K. That's a more mathematical term. Signature means the difference between positive and negative eigenvalue. And the signature of K is given by this. Yeah.
So you say other basis transforms, the determinant can change, but the signature.
Yeah, exactly. No, and the base transformation determinants also do not change. The let me just say this. Yeah, there are only certain base transformations allowed. In this case, we only allowed to do base transformation using the integer matrix with a unit determinant to do base transformation, so that I don't change the determinant of K. Yeah. Okay. So this is just some example of a bosonic topology order. But the main motivation is to introduce this E8 topology order. It's a very strange one. And probably it's more interesting to say, since we talk about the non-abelian anions. So therefore there should be non-abelian topology order. And also especially experimentally, how likely we can make this non-abelian topology order. Okay. And so here is that let's using this chi-m to describe many body wave function with m field lambda level. For example, this is the picture for the many electron states with 2 field lambda level. So their ground wave function will be chi2. Yeah. So chi2 just describing this kind of wave function. Okay. And the chi1 is just like a Laughlin wave function, but with the exponent 1. Okay. And then you can discuss a more general wave function. So the Laughlin states like a chi-m. This Laughlin state can view the chi1 to the m's power. Just chi1 to the m's power give you this wave function. So we can generalize a little bit. Instead of chi1 to the m's power, why don't we do chi2 to the 3rd power? Or more generally, you can do chi2 to the 2nd power, but that became a symmetric wave function. Then we multiply chi1 to make it anti-symmetric. So that's another anti-symmetric wave function. This should be electron wave function. Certainly, if you don't multiply chi1, this also became bosonic many-body wave function, will be with a similar property. Okay. So what is interesting is that when you consider wave function like a chi2 cube or chi2 cube or chi2 square, this gives rise to non-abelian statistics. Okay. And in particular, the effective chain summation theory for this is SU2 level 2 for the second case and SU3 level 2 for the first case. So this kind of yeah, that's how we know at the beginning why this is a non-abelian states. And there's another way to construct non-abelian states. We can start with this bosonic Laughlin wave function. And we want to make them anti-symmetric by including this p-wave pairing. So this is p-wave pairing. This is Z1, Z2, Z3, Z4, they're p-wave. But with the pole. But the pole is okay because this will have 2 zeros. A single pole is okay, can be absorbed by the single. So this is still legal wave function. And this A means totally anti-symmetrization. So actually the first part basically is a BCS wave function with a p-wave BCS wave function. Then multiply this Laughlin wave function. We can construct, we call the Farfin states. And this wave function happen to be the correlation function of some CFT. And the CFT conformal field theory have conformal blocks. From there, we can see this wave function have a non-abelian statistics. So you can see the non-abelian statistics at the beginning is obtained in a very strange way. Okay. And in particular, I want to say that for this wave function and for this Farfin wave function, and they have a quasi-particle. It's called Ising anion with a quantity dimension square root 2, we just mentioned. And for the first wave function chi2 to the third power, the anion is a Fibonacci anion. The quantum dimension is square root of 5 plus 1 over 2. So this is even more strange. Yeah.
Does this multiplication of the many-body wave function, is that something physical? Some physical process that corresponds
Yes.
to?
Yeah, that's the next slide. Yeah,
Okay.
we'll do that. Yeah. So at the moment, you can imagine as a toy model, we have a ground wave function. Then we need to design the Hamiltonian such that this wave function is a gap the ground state. This part is tricky and but probably doable. Yeah. And
Hey, just check out, so actually when you go 1/2, I guess it's experimentally there's no gap state there. Like, when you go to 1/2.
there are depends. Maybe let just a moment. Maybe I'll address the question just a moment. Okay. So at this stage, we just like a theory, just a toy model to see non-abelian statistics is a possibility. Okay. So now the question is that how likely you can realize this wave function? That's a question. Or maybe before that, let me explain why the particles have non-abelian statistics. Why quantum dimension is more than 1. Okay. So we're using this wave function. It's a chi1, chi2 square as example, which basically chi1, chi2, chi2. Okay. And then what the game we play is the following. So chi2 is a 2 lambda level field. Okay. And we can create a 2 hole in the first chi2 and the 2 hole in the second chi2. Then multiply them together. So this is the wave function. So this chi2 x1 x2 means this is 2 field along the level, but with 2 hole at x1 x2. The second one is a 2 hole at x3 x4. Yeah, that's just this picture. So when you multiply them together, you get a many-body wave function with 4 particles, 4 quasi particles. Then certainly, suppose this red one is x1 x2, the blue one is x3 x4. So in the second chi2. So these two are the same because these two wave function, it just exchanges the red chi2 and the blue chi2. And when you change them, it's still same wave function. So actually you can convince yourself these two wave functions actually is the same wave function. But however, this wave function and that wave function is different. They are different. And because it's these are 2 red one in the first chi2 and 2 blue one in the second chi2. They range differently. And the third one, the fourth are also different. So these 3 wave function looks different. So as a many-body wave function, they are not same one, maybe orthogonal. But if you look at each in the neighborhood, each quasi-particle and also neighborhood without any quasi-particle. And I don't know, maybe you need to believe, but I believe it. So it's they are the locally wave function looks the same. Sometimes I don't know how to make a rigorous mathematical statement. I just believe it. So this is the one moment. It's just in the neighborhood of every quasi-particle. You don't care which one. It's like the first one or second one. So it looks the same. Without any quasi-particle, it's just like ground state. It's also the same. So this makes it plausible that these 3 states happen to be the wave function 1. They are locally indistinguishable, but globally orthogonal. So that is really source of topological degeneracy. So because they have this wave function have some entanglement. So such thing exists. When you have entangled wave function, you may have 2 orthogonal wave function. They locally looks identical and indistinguishable. So here, this is a way to construct such a orthogonal wave function, which is locally identical but globally different. I think in reality, the story is more complicated. Actually, we don't have 3 states. We have 2 states because these 3 states are turned to be linearly dependent. There's one linear relation. So but we do have 2-fold degeneracy. So these 3 configurations derive 2 orthogonal states. And so this is the argument to say that these 4 quasi-particles have internal degree freedom is 2 dimensional, have 2 states. So something very strange. You know, 2 is not the power of 4. So you have to assign something non-integer for each particle to produce 2, you know. And then you may say each part, if there's these 4 particles have a 2 degeneracy, each particle should have quantum dimension 2 to the quarter power, not square root of 2. But if you look at the formula, we have a beginning. There's overall 1/2 here. So that's another subtlety. When you have a 6 particle, 8 particle, you can discover actually there's an overall 1/2 factor. So actually each particle have a square root 2 degeneracy. So this is this kind of a beginning. I think Chetan Nayak and Frank Wilczek have a paper which studied this very carefully and get these results. Yeah. Okay. So this is a way to understand why this kind of wave function produce non-abelian statistics. Yeah. Okay. And so now the realization. You know, how do you realize this this non-abelian statistic? Whether this wave function is practical or not? Okay. So actually the wave function, the wave function, the first order level, if you read it in terms of complex coordinate, they are just like only have z. But the wave function in the second order level would have z bar, you know, as a prefactor. You know, you always the Gaussian, but the wave function in the second order level would have a z bar. Okay, so this is what I'm going to use. So now let's look at this wave function. So this chi1 cube means this prefactor only have a zi minus zj to some power, always holomorphic. So this cube also belongs to first order level. This wave, in this many-body wave function, every electron in the first order level. But there's another wave function that's a chi1 squared times chi2. Then this wave function would have a single z bar for each electron, have a z bar, single z bar for one electron. So this wave function would live in the first 2 lambda level. But so there's some component of this wave function live in second lambda level. And this wave function have filling function 2/5. Actually, we believe that the observed the 2/5 quantum state with filling function 2/5 really is like kind of like this wave function. But these have an abelian statistic, no non-abelian. Now from this you can see that chi1 to the chi2 to the square. Then this z bar appear twice. When z bar appear twice, actually this wave function live in the first 3 lambda level. But mostly they live in the first lambda level, but there are some component live in the second and the third lambda level. Okay, and this is a good hint. That is, if you engineer my device, the first 3 lambda level are degenerate. If first 3 lambda level are degenerate, then with the Coulomb interaction, this wave function is very favorable. Because you can see chi1 is an electron wave function, chi2 also electron wave function. Means in this wave function, when 2 electrons bring together, there's a first order 0. When you do this wave function, chi1 and chi2 squared, when every 2 electrons bring together, you have a third order 0. The electrons stay away from each other. And this can be achieved only if you allow electron occupy first 3 lambda level. So every pair electron has third order 0. So Coulomb interaction is very happy. Okay. So I can imagine that if first 3 lambda level degenerate with Coulomb interaction, this wave function will be a happy wave function, maybe a very good ground state. And that's just as stable as the Laughlin states. And that is non-abelian states. Okay. And so this is the proposal. And if you make a first 4 lambda level degenerate, then you get this Fibonacci non-abelian states. This one is the Ising non-abelian states. Okay. So one may say, okay, maybe it's hard to make a 3 or 4 lambda level because we can use a spin, electron spin as an index, as a lambda level index. So maybe we have 2 lambda level with plus 1 spin. Maybe a 2 lambda level degenerate plus electron spin have been done like effectively like a 4 lambda level. So that's also kind of true. But the spin degree freedom is trickier. You know, the power wave function we no longer have third order zero, this kind of argument. So multi-component is trickier. We need more design. Yeah. So you know how to make a first 3 lambda level, 4 lambda level degenerate. You have to engineer this dispersion relation, not parabolic. I mean, parabolic with some wiggles. You have to really, yeah. This became hard. Yeah. So this is so this may not be that practical, but also probably not that ridiculous. You know, so that's one thing. Then about this filling from one half states. Why filling from one half can be non-abelian? Actually, they are not non-abelian. Indeed, they are gapless. But that's even only true for the first order level. We have filling fraction 1/2 in the first order level. Then this Coulomb interaction will make filling from 1/2 states a gapless states. But however, in the second lambda level, the Coulomb interaction is modified by the electron wave function. I think second lambda level electron wave function is more like a circle. So the Coulomb interaction is like a 1/r weighted by the circle. So actually the shorter interaction are kind of different. We call the soft core. The hard core repulsion became weaker in the second lambda level. And this became important. Then if electron live in the second lambda level, and we have filling from 1/2 at the second lambda level, they may be gapped. Actually, they are gapped. So experimentally show is gapped. In the first lambda level, filling from 1/2 is a gapless. Second lambda level, filling fraction 1/2 is a gap. So then, so therefore, so this gap state maybe this state is a 1/2 filling from 1/2 states, maybe something like so. This gap state maybe this SU2 level 2 states, or maybe it's a Fabin state, or maybe some other state. So actually there's some ambiguity here. That is at a filling fraction 1/2, we could have this so-called 3-3-1 state. That's K matrix, whose diagonal element is a 3-3, and off diagonal is 1. So it's 2x2 K matrix gives the 3-3-1 abelian state that also have a filling fraction 1/2. But however, this state also have filling fraction 1/2 and a Fabin state as well. So there's a bunch of states with filling fraction 1/2. And they all have same non-abelian anion, Ising non-abelian anion. But there are some slightly difference, like this Chi1, Chi2 square states and this Fabin state, they differ by their boundary. The boundary have different boundary mode. Okay. So how to understand this boundary mode? How to understand this difference? Actually, the easiest way to understand this difference is there are 2 ways to understand the difference. Both are easy. One way to understand this difference is the following. In this kind of state, there's a neutral fermion. So the electrons fermion and they carry charge. But this non-abelian quantum Hall state is an Ising topological order, have a neutral fermion. And then when the neutral fermion form a lambda level, they don't change filling fraction, they don't couple electromagnetism. But when neutral fermion form lambda level, they generate the edge states. So all the states are different by this neutral fermion may form different lambda levels. So the edge states differ by 1 mode. So this C is the number of edge mode. So this they differ by 1. It's just that this neutral fermion have a different integer quantum Hall states. Another way to understand this is the following. You know, at the filling from 1/2, there's another possible gapless states where you have a composite fermion form a Fermi surface, the Fermi liquid. Okay, I think Jim studied this a lot. And so then this Fermi surface, the composite fermion, may undergo pairing and became some kind of paired DCS states. And that pairing states make a gap, and that pairing state like can be P plus IP is this one. and can be P minus IP will be this one. And for this one, maybe it's not P plus P, maybe, I don't know, PDF, maybe F plus IF, you know, it's a more angular momentum. So this is parent may have a more angular momentum. So this state is like a F parent state. This is a P wave parent. This is a minus P wave parent. You know, so that is a so this is another way to understand all this sequence. Okay. And so therefore this maybe this is a one of the closest case we may have a non-abelian states that is fitting from 1/2 quantum Hall states. And so the key is following to measure the number of edge mode. Here is 1/2. So that's another thing kind of strange. Usually when you have a mode, you know, mode just one, like a integer quantum Hall state, you have a complex fermion, there's one mode. So this mode C actually is counting how many density wave, how many phonon. So C equal to 1 means that we have a single one-dimensional phonon. It's like that. So therefore, like for this abelian state 331, the C equal to 2 means you have two mode. Two mode means that this quantum Hall state like have a two component fluid. Although we have only one kind of electron, but for some reason, electron automatically, spontaneously became two types. Each type forms its own fluid. Then the fluid, bounded fluid, you might have waves. And that dense wave, this fluid just gave you one mode of phonon. So that's two mode. Okay. And however, for non-abelian states, it's kind of funny. We can have half mode or quarter mode or some kind of fractional mode. Yeah. And in this half mode, this case is easy to understand because we can describe a half mode using Majorana fermion, and which give half mode. But sometimes you have a not half mode, have a quarter, 1/3. Then it's hard to use a Majorana fermion. Then it's something really you have to use something more sophisticated CFT to describe it. But yeah, that can be done. So the key to expand and measure this number mode is using the thermal Hall conductance, because the mode is chiral. When the different edge have different temperature, then you may have heat current proportion to number of mode. Yeah. Then let's realize that you have a transverse temperature gradient. Like here, this edge have a higher T1, this edge have lower T temperature. But the heat current is perpendicular to temperature gradient. Heat current is going up and down. And this kind of thermal Hall conductance. The thermal Hall conductance is a way to measure number mode. It's a good thing about this that they do not depend on boundary velocity. The velocity somehow cancel out when you do the thermal Hall conductance. Another way to measure this mode, you can measure the heat capacity. The boundary have heat capacity, but the heat capacity depends on velocity. And you don't know, if you don't know the edge mode velocity, the heat capacity don't tell you how many modes are there. But however, the thermal Hall conductance, this velocity cancels, so you can just directly measure, like this heat capacity depends on this velocity here. But the thermal Hall conductance, the velocity cancel, so there's no material dependence parameter. So you can do that. And amazingly, this Hebelin did that. This is maybe one of very difficult experiments, and I kind of forgot. You can see the design is just amazing. They can do that, and they have do this at 50 millikelvin, such a low temperature, and to do this very, very sensitive measurement. That's I don't know, because this is a noise measurement. The noise measurement, you need to have some kind of cable. The coax cable in television is 50 ohm. I don't know, I think to this kind of device, 50 ohm like a glass of an oven. you lose everything. So they have to use some, I don't know what the trick they say. They can measure the noise, and with such low temperature, I don't know, maybe currently his only group can do that. So this is apparently not repeated. So that's a problem. But anyway, they measure this some value like that, and suggesting the number mode is not quite a half, but 5.6 or 6.4, and 7.6. Actually, at the lower temperature, it's getting worse. So we pick this data. No, there's a reason, you know, at low temperature, there's an impurity have more effect. So, but anyway, so there's some evidence. I cannot say this is a smoking gun, but this is a one of a more direct measurement to directly measure this central charge, and almost like direct measure non-abelian property. So this is yeah, this is the thing. Certainly, we wish there's a more things. Yeah.
It's suspicious that the ratio came out with the Wiedemann-Franz ratio, right?
Huh?
It's suspicious that the ratio came out. They're not something interesting, but the usual Wiedemann-Franz law.
Oh yeah. And oh, I see. You say did you happen to agree with this Wiedemann-Franz law?
Always candidate wave function. Right?
I see.
Only one of them has C equals to B, right?
Yeah.
The one that uses exactly the Wiedemann-Franz type prediction.
I see. Yeah. Yeah. This is a. I don't know. This is a situation that the theory is ahead of experiments. So experiments know what to look for, and that sometimes can be dangerous. And it's not like this integer quantum Hall states. Experiments find some strange value, 25 kilo ohm, and later this can be expressed by fundamental concept. That is more. Anyway, yeah. So this is a kind of situation, and actually, this kind of maybe I may make several remarks. Is that I feel that this higher lambda level is a place to looking for non-abelian statistics or non-abelian states. That's one thing, but this is explored. But another thing which is not quite explored is that in the graphene sample. And the point I want to make is following. You can see theoretically, we say first lambda level, second lambda level is same. Yeah, they're similar. But in experimentally, they are different because of the Coulomb interaction are modified differently. And this detail is important. And in the first lambda level, because there are special Coulomb interaction, we see this main sequence of a fractional quantum appear in the main sequence, in some sequence. And the appear in the sequence means that we may also only see abelian states. But however, in the second lambda level, this main sequence of a fractional quantum state is not that clear. It's not clear at all. Let me see what I think I may have a picture for that. Yeah. So you can sequence is like a 2/5, 3/7, 4/9. They appear in some pattern in the sequence. So that's on the main sequence. Okay. So this feature gave rise to abelian quantum Hall states. But in the second lambda level, the sequence is kind of broken. When the sequence is broken, that means interactions are strange. You may have more chance to see non-abelian states. Only in second lambda level. I think in the graphene sample also have a lot of quantum Hall states, and maybe even more with higher energy scale. In the graphene sample, we don't see this main sequence. The sequence is very strange. And suggesting that maybe interaction in the graphene maybe is kind of strange. So maybe there's a better chance to see non-abelian states in graphene sample because the interactions are quite different. Yeah. And but unlike the early days in the 1990s, where everybody working on quantum Hall states, although the graphene have a lot of data, but you know, there's many other things happening. So not too many people working on the graphene, and so maybe there's chance. Maybe graphene sample probably have good chance to be. Yeah, if you look at more carefully, maybe it's there. So right now we only have this at the 1/2. It's very weak. You can see that the weakness is the data, this is data. That's evidence you can judge for yourself, how strong that is. Yeah. Okay, I think I will stop here, and that's a natural place. Yeah. So any questions? Yeah. Okay, yeah, if not, maybe we can just end here. Yeah.